Good afternoon, DEF CON. What do we do with first-time speakers?
Woo! Here we go. Here we go! I needed this.
Ladies and gentlemen, Elvia.
Thank you guys to be here. It is amazing experience to be here for my first time. And let's talk about EDR, XDR bypassing. First of all, our agenda, a little bit who I am, a little bit what is hook chain and what is not hook chain is, and these research limitations, and after that, let's talk about the basics to understand how does hook chain works, and after look through hook chains itself. Who I am? My name is Elvio Jr., aka Maverick. My undergraduation school, I did an airplane pilot, so yes, I am a pilot, and I was the first in America Latina to earn OSCE 3, and I studied, or maybe studying to OSCE, this research that I have no much time to study OSCE, and what I like low-level exploitation, buffer overflow, shell coding, malware, and so on. And also, I am CEO of Sec4Us, a company, a Brazilian company that provide training and researching, consulting, and so on. What is the motivation of this talk and this research? Many people believe that I have solution X, that I top of the Gartner, and I am 100% protected. No, there is no silver bullet, and when I doing pen testing or red team exercise, I just need to bypass your environment. I don't need to bypass everything, just your environment. So, and full undetectable. Sometimes it happens. And what is hook chain? Hook chain is a technique. It is not a tool. I'm not pretending to launch a tool. Yeah, obviously, I need to do some programming. I need to create a code to prove the concept, but it is a technique, okay? And what is the focus of hook chain? Do bypassing of monitoring of EDRs and the XDRs inside of any TDLL. In other words, 100% user land. Nothing about kernel land, okay? And limitation. As I said, it is 64 bits programming and limited just to NTDLL user lane hooks, and I'm not pretending here to classify the EDR vendors, XDR vendors as his effectivity. I'm just launching a new technique, okay? I need to do some tests, but I'm focused just in one point, not entire ecosystem. So I'm not pretending to classify EDRs. It must be clear for all guys. During this study, I did a public call for vendors to work together with me to get early access to this code, to this technique, and no one answered me. When I published some bypass in LinkedIn, I received some calls, not too happy calls sometimes, but I received just 3 weeks ago some calls in order to test this. Okay? And let's go to the technical things. First of all, we have almost 2 layers in order to protect and split the time inside of our operational system. Ring 0, kernel land, and ring 3, user land. To transition between user land to kernel land, in a few words, we have just one way to do this, using a gate calling system call, or system dispatcher, and so on, that I can transit from user mode to the kernel mode. In general, we have this picture where we have user proxies, system services, and so on. Doesn't matter what is his level is. It is a system level, administrative level, or a simple non-privileged user proxies. Every time I need to do this transition. In general, this is a responsibility to NTDLL to do this for me. So this is a common stack call where I have one common application that need to be, for example, need to execute first a virtual alloc to allocate a memory, and the common stack call, the application will call this from kernel 32 DLL, and the kernel 32 will call another API inside of NTDLL, and the NTDLL will prepare stack call parameters, register parameters, and we will execute assembly instruction called syscall that will transit from user mode to the kernel mode. This is just another image to explain that. So I have the user mode application, and the important here, system service number. There's a table called system service descriptor table where I have indexes from 0 to, I have no idea how much, more than 400 numbers that match each ID from a pointer to a kernel function. So when I need to transit from the user mode to kernel mode, I put the system service number inside of register RAX. Sorry about the English, but I put this number in this register, and I execute the system call instruction. And system call will comes to the kernel address space, and this function will match inside of this table and get the pointer to the real kernel function. And the real kernel function will be executed and return to the user mode space with the return of the executed function. Doesn't matter what this means. This is another image to illustrate that. System service call, system service dispatcher, the table with the indexes and the pointers to the function, and the real code through the function. Okay? And when I execute some proxies, unexecuted, or when I load DLL inside of another proxies, when I initiate a proxies, several actions have been done behind the scenes. One of the most important to this talk is related to import address table. Import address table, in a few words, it's a table that have the name of the function that I want to execute. For example, create proxies, and the name of the function, and the ID representing inside of this table, that when I run this, when I run the application, the operational system, the loading of the operational system will look through all loaded DLLs and fill this table with the address, the real address of this function in the operational system. Virtual address, of course, but the virtual address. So when I try to execute this process, my application will comes to the import address table and request import address table. What is the real virtual address to this function? And put this, for example, in a registry, and after that call the address of this registry in order to call the real function code. And another things that image loader do is look through the loaded DLLs if these DLLs was already loaded, recursive loading, and so on, and fill this function pointer. There is another image of was already loaded, recursive loading, and so on, and fill this function pointer. There is another image of hooking. We must say that the techniques that we use to attack, it's the same techniques that the EDR vendors are using to protect. Publish something related with these techniques in Windows 95. So a few years ago. And what is hook? Like interception of the stack call. When I try to execute some function, this function I'm not executing the real function. I will be intercepted and redirected to another function, like a man in the middle. In this case, it will be a function in the middle, but it's the same concept. Okay? The most common techniques to do that is using instruction jump or call, or I can use import address table hooking. How can I do that? Let's see. Talking about jumping, this is a strategy that that we can see here. It's the most common strategy used by EDR and XDR vendors. That is, when I run an application, NTDLL is the first DLL that is attached to my proxies. And after that, the EDR DLL will be attached, and the DLL from EDR will patch or change in memory the instructions of the NTDLL. So when I try to execute, for example, this function is changed to jump to address space of EDR code, in order that the EDR can check our parameters and response and so on. This is an example of original execution flow, where when I get the address of the function, the target function, we will receive the real address. But if after the EDR changings, or after our change, that because we will change this table, after that, instead of receive the address of the real function, the original function, we will receive an address to a hooked function, or to a function in the middle in this case. Okay, so we will receive a malicious function, or when an EDR doing that, the address of the EDR function. So when I call this address, we will call the receive the function. In this case, arbitrary code from EDR or from our perspective, and it is a decision if we will or not execute the real function. In talking about EDR infrastructure, the EDR will analyze the parameters and decide, yes, Elvio is a good guy, I can allow this. Oh no, Elvio is a bad guy, let's drop this. And pop-up alert and send this to SOC and so on. Okay? This is that I am talking. This is when the ADR load ADR puts another DLL, and it will be redirected and decide yes, no, execute or no, and do if yeah, Elvio is a good guy. Let's permit this execution. So do system call in kernel land. It's everything as usual, and after that come back to the user land process. Okay, I can see here an unhooked API. Okay, so I can see these typically instructions where there are moving from RCX to R10, and after that there is an ID here in hexadecimal where I put this ID in EAX or RAX, doesn't matter. And after that, there is a system call. This is a typical code from NTDLL's functions that will translate from user land to kernel land. And here we can see a hooked API where he is unhooked and he is a hooked API. As you can see, there is no this typical code. There is a jump code where I'm doing a jumping or an interception to the API or to the EDR code. Okay? Said that, the most common bypasses is remapping NTDLL, but to do that we need to load the NTDLL from the disk or from the another memory area. It seems to be malicious in most of cases. Another technique, it's direct syscall, when instead of goes through NTDLL, I get the system service number and execute the system call inside of my process. This sounds malicious again because the system call was not coming back from NTDLL memory address space. It's coming from my application address space, okay? And EDR catch this. Indirect syscall, it's similar to direct syscall, but instead of do system call instruction inside of my application, I will jump to an address inside of NTDLL that exists just system call instruction. So who will execute? NTDLL. So sounds less malicious. But in this case, the stack trace will be broken because I'm executing directly from my code inside of NTDLL. In general, the application doesn't do that. The application in general calls System32DLL, kernel-based DLLs, GDI DLL, and so on. And this DLL will call NTDLL and etc. So sounds malicious. Then there are amazing guys. Without this research, this talk today was not possible. So this is amazing guys created Heaven Gate technique, Hell's Gate technique, and Hallows Gate technique. So for this research, I used the part of Hallows Gate technique in order to resolve dynamically the system service numbers. Okay, so let's understand a little bit better about Hallows Gate, this part of Hallows Gate. In general, Hallows Gate locate the current address of the target function, the function that I want to execute. For example, create a virtual memory or create proxy and so on. And look that code that we saw, the typically code, and check if the typically code match with these structures. If yes, okay, this function was not hooked. If no, the function is hooked. Okay, so we can see that and how can I get the system service number? If the function is hooked, the real code, there's not exists more there. How can I see this? Let's see another screen here. We can see that the functions are linear. So we can see here, for example, the system service number 6, system service number 7. This function is hooked. So in general, I have no idea what the system service ID of this function. And the next function will be 9, and the next function will be 10. In other words, we can see the neighborhood functions before and after our desired function in order to calculate. If this function is 6, that function is 7, my function will be 8. So we can dynamically check this. This is Hollows Gate technique, okay? And before this research, this study, in a sunny day, playing with my two boys, my two kids, I have an idea. Whoa, the major part of EDRs are hooking in NTDLL. If I step above and try to catch or try to do a function in the middle, changing the flow before NTDLL. Okay, because several EDRs are checking if we are changing NTDLL. So because they are changing there, the EDR are checking if we also change there and flag us as malicious. So if EDR are checking there, and what if I did or I do this in a step above? So to check the viability of this technique, I create a code in order to check the EDR's hookings. So 9% of the EDRs are hooking just in NTDLL. So the technique can be viable. Okay? And I created the new technique called hook chain. What is hook chain? Hook chain, the first step, I will resolve system service number. After that, create a table where I store there system service number and an address of my custom stub function. In other words, the function that will be executed instead of original function. EDR do this. Whoa, I can do this also. And implant or change the import address table from our proxies to our custom stub function. And after that, continue as usual. With this, I have in more details the hook chain implant flow. First one, I resolve dynamically, map some critical functions because in this phase I had no bypassed EDR yet. So I need to use some functions not monitored by EDR in order to change some memory address and change some memory areas and so on, read and etc. So I map statically these main functions that I called here critical functions, and after that I create a table. We will see the structure of this table later on. We create a table that holds system service number that I already mapped, the function address, the real function address inside of NTDLL, and the closest address that holds a system call instruction inside of NTDLL. And after that, I preloaded some functions. For example, if we will run Metaxploit payload or Havoc payload, and I have no idea. There are another DLLs that must be called before the execution of this payload. Because a simple executable, for example, has no access to the URL APIs or crypto APIs. So we must preload this DLL in order to change the import address table of this DLL. So here we preload these DLLs, and after that do the magics. Change the import address table of all needed DLLs. In this time, I need to say that there is not a good idea to change the import address table of all loaded DLLs. I tried that, and I lose my hair trying that, and that's not a good idea. believe me. So I created like a blacklist DLLs where I put inside of the application and do this preloading, and after that changing that. This is the typical flow after hook chain planting, the simplified version. So my application must call virtual unlock, for example, to create a malicious area in order to put their Metaxploit shellcode, for example. And I need to create this. I will call kernel32 DLL. Instead of call direct ntdll, this function, as I hook it, as I did a function in the middle, this flow will be redirected to my application stub code. This application stub code will check several things and create a stack frame, a stack call, put the information inside the registers, and after that do an indirect syscall in order to execute. And kernel mode as usual. Here, I can present you the first struct that I will use. I will use here a list, okay, with this system call information, and each entry of this list has a system service number, real address from the real function, okay, the address of the function, or the address that holds the system call instruction, and the address of my stub function that will be redirected to. And a hash used to bypass static analysis instead of the name of the functions and so on. Okay? And this is the entire flow, where the same, my application wants to execute some function, we'll call kernel32 DLL, and that call kernel-based DLL, and after that, I will check in an import address table. When I check in import address table, instead of receive the original address, I will receive my stub function. So the application will redirect to my stub function. Inside of this function, I can check the system call list, the list that I saw, and the list, there are several items in order to check, get the parameters, the real function, syscall address, and so on. Create the stack call frame and put everything that we need in the registers, and after that do indirect syscall. Okay? What are the advantages of that? How this works? Why? Reduction of probability to identification for several reasons. The first one, total time of execution. As I have several times similar to the regular execution, the ADR cannot flag us, because the total time of execution, the telemetry of total time of execution will be okay, will be seems to be valid. And stack frame. Talking about stack frame, I'm execute as usual, coming from kernel 32, for example, kernel base, and so on. So I'm not stepping steps, not skipping steps. Okay, and the most important, I did not, or I didn't need to change the code of the original application. For example, we will see in demo, when I want to execute Mimikatz, for example, I don't need to touch the code. I just execute the hook chain in order to implant and execute Mimikatz. That's it, because the hook chain implant and everything that we need, the function in the middle. Let's see the first demo where we will execute and command and control using Havok. Okay, this is flag as malicious as usual. And let's see this first one. Here we can see Bitdefender updated with advanced threat protection full enabled, and in the left side we can see our console where we will have, let me see, let's stop here, just let me put here together in order to, okay, no problem. First time we implant hook chain. After that, download remotely from HTTP the malicious payload, and after that execute this malicious payload. So we are using Havok to do that, and here we go. Executed our first command control. We can interact with that without any identification. Thank you guys, you are amazing. It's just a starting one. Let's go back to the presentation. Whoa, here it is. Looking in details, we have the first step is mapping everything that we need. So in this operational system we have 472 NTDLL functions where we can map, and these functions are hooked, or I need this as a critical function. And after that I create this table, okay, import address table, hooking. So I can see here the output of these hookings in kernel 32, kernel base, user 32, and so on. Let's talk about the real environment. First of all, thank you for our friends, our Brazilian community, that there are most guys here that share with me your environment license and help me and support me in order to make this research works. Without you guys, nothing will be possible. Thank you so much. And because obviously some EDR vendors are not too happy and not sharing their licenses or their environment in order that I test. So there are a lot of friends sharing his environment with me in order to make this test. Okay, so we did this in a closed environment. As the focus of this research is talk about EDR protections, and we will touch here LSAS. I disabled the run as PPL and coordination guard inside of the Windows because the target, the full focus, it is not the Windows. It's not the EDR and the XDR products. So let's execute the second demo for you guys. The same as again, we have the antivirus, EDR working with advanced threat protection, and we will execute as usual Mimikatz. I downloaded from GitHub, put on my server, as you can see, and execute this guy in a protected environment. And let's see this working. Woo! It's not wow. Execute and show a coffee. It's the easiest part. Let's dump the creds. Without creds, we have nothing. So, yeah, we can touch the LSAS without any identification with regular Mimikatz, guys. Woo! Coming to the end, we are able to test with 66% of the products present in Gartner, and in additional 4 other products. And this is the result table. Okay, we tested remote proxy injection, Meterpreter, and Havok as non-privileged user, and Meterpreter loading QE model, Mimikatz, ProcDump, and a custom 100% developed by me, 100% assembly LSAS dump. Okay, I create this in order to do these tests. And this is the result table. Okay, this is the products that I was able to test. And as you can see, we have a lot of effectivity in order to doing these little things. As I told you guys, 3 weeks ago, 2 vendors reached me in order to test again. The Sentinel one was the first, and the second was the Trench. These results that I'm showing you, the Sentinel one was able to stop hook chain. They did some patches in his product, and I was able to test this and stop it at all. Okay, deadline, end line. And the trend is still working on this identification. Identified some behaviors, but not at all. Okay. The other vendors, non-contact. Okay. I loved this phrase of Steve Hawking. I'm just a child asking who, how, and why. Occasionally, I found the answer. Thank you, guys. This is my contact, full white paper, source code, reference, and feel free to contact me. Feel free to reach me by LinkedIn. My LinkedIn, it's my name, just Elvio Jr. And that's it. Now it's your time to ask questions. Thank you.